Okay, so in this video we're going to dive a little bit deeper into the requirements for aromaticity to see if we can understand this in a much more detailed way. So what you need to get to aromaticity are several things. The first thing is uninterrupted cyclic conjugation. Okay? So that's something that we sort of touched on in the last video, where you need basically a p orbital at every single carbon of your aromatic ring. The other thing that you need, and this is in some ways saying the exact same thing, is that the molecule needs to be essentially planar. And that just has to do with the fact that in order to get conjugation, you need those p orbitals to be aligned with one another. They need to be parallel. If you have perpendicular p orbitals, they cannot be conjugated, and any angle between them is a reduction in conjugation. So to get full conjugation, you need parallel p orbitals, and so that means that the whole conjugated pi system needs to be planar. So these two things are essentially the same thing, but is worth splitting them up. And then the third thing you need, this is this magic number of electrons. Okay, so what is that magic number? Well, it turns out that the magic number is given by this formula, which is 4n plus 2 pi electrons, where n can be 0 or any integer. Okay, so what that equates to then is that if you have 2, 6, 10, 14, etc. electrons in this uninterrupted cyclic conjugation that is planar, then you're going to achieve aromaticity. Okay, so that's the magic formula for the number of electrons. So let's walk through each of these things in a bit more detail. And before I do that, so this rule here, this magic number of electrons, is called Huckel's rule, after Huckel, who first sort of defined this. So it's usually called Huckel's rule. That's what I call it. Sometimes you'll see it as Huckel's 4n plus 2 rule, which is just a bit more awkward. Okay, so let's go through each of these in a bit more detail. So again, this is the picture of benzene that we saw in the last video. And as we talked about, each of the carbons has a p orbital. So we have a p orbital at every atom in the ring that's involved in this conjugation. Okay, so that's good, and so benzene obviously satisfies that criteria. And of course, we know benzene is aromatic. On the other hand, if we were to look at this molecule, so this is cycloheptatriene, you can see that there's an atom here that's saturated, right? So that there is no p orbital here, and that means that we don't have full conjugation around the ring. So this is not an uninterrupted conjugated pi system, and therefore it can't be aromatic. And in fact, this molecule does not display any of the characteristics that we know to be associated with aromaticity. Okay? Planarity. Again, this is very much related to this conjugation, but we can look at this in some other molecules. So again, we know benzene to be planar and aromatic, and we talked about actually this first one here, cyclooctatetraene, which is not aromatic, and it is in fact not planar. So as we showed in a previous video, this is actually tub-shaped, right? So these pi systems, each of the individual alkenes is not conjugated with its neighbors by virtue of the fact that those single bonds between the alkenes are actually rotated, such that they're essentially orthogonal, and they do not have conjugation. Another molecule here, so this is cyclodecapentaene. This actually has the right number of electrons to satisfy Huckel's rules. It has 10 pi electrons. But it turns out that this actually can't be planar because of these two hydrogens which I've drawn in. So in order for this pi system to be fully planar, those two hydrogens would actually have to occupy the same space. And of course, that's not going to be allowed. And so this pi system simply can't achieve planarity, and therefore it can't achieve the full cyclic conjugation. So this molecule, unfortunately, is also not aromatic. Okay, so planarity is a requirement for full cyclic conjugation. On the other hand, if we just make a slightly bigger system where every atom has enough space, such as this rather large looking molecule, This, in fact, is planar, and it has the magic number of electrons. Okay, so here everything is quite happy to exist in a plane, and therefore we have full conjugation, the right number of electrons, and that actually is an example of an aromatic ring. Okay, let's look at this final one, this number of electrons. Okay, so we can give examples of molecules that don't possess the magic number and that do, and you can see that they just alternate quite nicely. So for example, if we have 4 pi electrons, that doesn't fit with 4n plus 2, right? And cyclobutadiene is not aromatic, as we've come to understand. Benzene absolutely is aromatic, so it has 6, so that would be where n is 1, so 4 times 1 plus 2 is 6 pi electrons, and of course we know benzene to be aromatic. 8 does not fit the rule, cyclooctatetraene is not aromatic, and 18 does fit the rule. Okay, so we can see examples, and there's many more examples that we could give, but that's the pattern for the electrons. But okay, so that's just an empirical result, but the question is why? Why is this magic number of electrons so important? And the very short answer here is that it has to do with symmetry. It has to do with symmetry on a quantum mechanical level. Now, fortunately, we don't have to go into quantum mechanics to understand this, but what we do want to look at is molecular orbitals. Okay, so at this point, if you are not feeling confident in your understanding of the molecular orbitals of alkenes or conjugated pi systems, I think it would be useful for you to pause this video at this point and go back to the book or go back to another video and quickly refresh yourself on how these molecular orbitals are arrived at. Okay, but assuming that you have a good handle on this, what I've shown here is the molecular orbital diagrams for a series of increasingly conjugated pi systems. So over here on the left, we just have a single carbon with a single p orbital, right? So this would be the building block with which we build all of the rest of these systems. So we're going to bring together a bunch of carbons, each donating a single electron in a p orbital. So if we want to build up ethylene, we bring 2 carbons together. And so if we bring together 2 p orbitals, 2 atomic orbitals, we have to get to 2 molecular orbitals. Okay? And so one of those is going to have full symmetry, and that's going to be the lower energy one. This is the bonding orbital. And then we're going to have the one that's antisymmetric, okay? And that's going to be the antibonding orbital. So that's above the 0 energy line here. Okay? So ethylene is very simple. If we go to 3 carbons, so an allylic system, okay, so like the allyl radical, we still have to have symmetry about the 0 bonding line. So we're going to have one that's full symmetry, that's the low energy one, completely bonding. We're going to have a completely antisymmetric orbital, and that's high energy antibonding. And then we're going to have one that actually has a node at the central carbon, and so that's actually going to have 0 energy. It's going to be non-bonding. Okay, we can go up to 4 carbons in 1,3-butadiene, and again, it's all about symmetry. So we're bringing together 4 atomic orbitals. We need to get to 4 molecular orbitals, and every time we go up in energy, we increase the number of nodes. So down here we have 0 nodes, completely bonding. The next one up, we've got a single node, okay? And then when we go up even more, we have 2 nodes here, and now this is an antibonding orbital. And then up here we have the maximum number of 3 nodes, and so that's the highest energy, completely antibonding. And you can keep going. So here's the 5-carbon system, and then the 6-carbon system. Now the 6-carbon system is actually quite interesting because this has the same number of molecular orbitals as benzene. But you can see what you have here is again, this sort of stratified system where each molecular orbital is at a higher energy and includes an additional node. So 0, 1, 2, 3, 4, and so on. Okay? And so we have 3 molecular orbitals that are bonding, and that very nicely will fit all 6 electrons that are donated from those 6 carbons. Okay? So we could actually conceptually think about building the molecular orbital diagram of benzene if we were to take 1,3,5 hexatriene and connect the ends. Right? So imagine if you did that. So in each of these molecular orbitals, we would just wrap the ends around and attach them. Now, as with any molecular orbital, you have symmetry requirements, okay? So that's going to dictate exactly how these molecular orbitals look when you were, if you were to attach those ends, okay? And so don't be too confused by that, but if that helps you to understand, then feel free to think about that. But so let's now transition to the molecular orbital diagram of benzene, okay? So here it is, all right? And you can see that this is actually significantly different, okay? And so what we have with benzene is first a single lowest energy molecular orbital where, again, this is the highest symmetry. This is completely bonding. Every single atom has a bonding interaction with its neighbors. That's the same that we saw with 1,3,5 hexatriene, but it's actually got an additional bonding interaction. So if you look at 1,3,5 hexatriene, you've got 1, 2, 3, 4, and 5 total bonding interactions between those 6 atoms. If we look at benzene, we actually have 1, 2, 3, 4, 5, 6. We actually have an additional bonding interaction. And so this most stable, lowest energy molecular orbital is actually even more stable because it's cyclic. It's got that cyclic conjugation. Okay? But what happens after that is significantly different from all the molecular orbitals that we saw in the last slide. Okay? So what we've got, instead of having this stratified one by one ordering of the molecular orbitals, here what we've got are degenerate pairs of molecular orbitals. Okay, so each of these orbitals that come at the same level are of equal energy. And remember that every time we put in a new node, that goes up in energy. And you can see here that at this first level, so here we have no nodes. At this first level, we have one node in both of these molecular orbitals. And it might be not so easy to see here, but basically you can see a node whenever the sign of the molecular orbital changes, right? So here there's actually a line that runs sort of down the middle of the benzene ring, and so it goes from green lobes to blue lobes in this picture. That's a node, and so anytime there's a node, there's not going to be bonding interactions between the different sides of the molecule in that molecular orbital. It's maybe a bit easier to see on this one, so there's also a single node here, and it just so happens that the node passes right through 2 of the carbon atoms in the benzene ring, and that's why we see 0 electron density there. But in both cases, there's a single node, and that's why they're at the same level. We can also see up here, so now we've got 2 nodes, so we change signs twice here. And it's a bit harder to see here, but again, we have one of the nodal lines passing through 2 of the carbon atoms. And then what we finally got is a highest energy molecular orbital where every single interaction is anti-bonding. So that's the highest energy orbital. Would be very destabilizing to have electrons there. Okay, so that's the molecular orbital picture of diagram of benzene. And it's very much impacted by the symmetry requirements of having a cyclic conjugation as opposed to a linear one. Okay, so it turns out though that actually every, well, before we do that, so here's just a different picture of the molecular orbital diagram of benzene. And this is actually a bit more realistic in that these would be actually calculated using quantum mechanics. And so they're a bit more realistic than these cartoon-looking orbitals. And here, hopefully, you can see the wonderful symmetry of the lowest energy orbital and the fact that each of these has a single node, each of these has 2 nodes, and here's the 3 nodes. So this is a bit easier to see, although you don't see the individual contributions from each of the p orbitals. Okay, so this is a molecular orbital diagram of benzene. It turns out that every single aromatic ring has this exact same general structure to its molecular orbital diagram. So what we have, again, with any cyclic conjugated system, actually any cyclic conjugated system, is the same pattern. So we're always going to have one lowest energy molecular orbital that has the highest symmetry, complete bonding interactions all around. Okay, that's always going to be the case. Then we're always going to have degenerate pairs of molecular orbitals of equal energy as we go up. Okay, so 2, 4, 6 as we go up. And then in the case of if you have even numbers of molecular orbitals, as we do with benzene, there's going to be one highest energy completely anti-bonding orbital. If there's an odd number of molecular orbitals, you will just end with one degenerate pair as the highest level. There won't be that additional one because we have to end up with an odd number of orbitals. Okay, so now imagine what happens if we start to fill these orbitals with electrons. Okay, so again, this is just completely generic here. We don't even know what molecule this might be. But imagine that you start to add in pairs of electrons. Okay, so if we add in 2 electrons, right, this is the first of those Huckel numbers where n equals 0. If we add in 2 electrons, that looks great because they both go into this lowest energy molecular orbital, which is completely bonding and it's extremely stable. So that's going to be a fantastic system if we do that. What happens if we put in 2 more electrons, though? We go up to 4 pi electrons. Well, based on Hund's rule, these are going to each fill in their own orbital, and you can see they're going to be unpaired. And unpaired electrons are very reactive, right? They basically act like free radicals. And so this is not going to be a good situation. 2 electrons good, 4 electrons is very bad. Okay, it's very reactive. But if we could add 2 more electrons in our system, we, again, would have completely paired electrons. All 6 would be paired, and that's actually very good, right? So again, 6 is the second Huckel number, where n equals 1. So 2 and 6 are good, 4 is bad. And we can keep going. So 8 electrons is also going to be bad because we're going to have 2 unpaired electrons in that next pair of orbitals. So the fact that we have these degenerate pairs of orbitals basically leads to sort of every other even number of electrons being good and every other being bad. All right. We sort of are still missing a final piece here, though, because it's not only just the fact that we have paired and unpaired electrons. The energy level of those electrons is actually very important, and this leads us to a wonderful, I'll call it a trick, but it's not actually a trick. This is a technique for very quickly getting the molecular orbital diagram of any aromatic or any conjugated pi system that includes not only the relative sort of general structure of the molecular orbital, but also the relative energies of the molecular orbitals. And this is fantastic. So this actually comes from quantum mechanics, and it's actually wonderfully mathematical. I think the ancient Greeks would have absolutely loved that this works. We're not going to deal with the math or how this actually derives. We're only going to deal with this pictorially. And so it's actually quite simple. So here's what you do for a Frost diagram. What we are doing, again, when we're building these molecular orbitals is we're taking individual p orbitals with a single electron and we're building up these pi systems, okay? So if you have an isolated p orbital, right, that's going to be non-bonding because it's not bonded to anything. So we always draw this dotted line, which represents the 0 energy line. So what we do for a Frost diagram is we put a circle that's centered on that line, okay? And then you take the size of the conjugated pi system you're dealing with, okay? And you inscribe a perfect polygon of that size within the circle. Okay, so for example, if we wanted to do benzene, benzene has 6 molecular orbitals, okay? And so we're going to inscribe a perfect hexagon within that circle, okay? 6 molecular orbitals, perfect hexagon. And then what we do is that at every vertice of that polygon that we put in, we put in a molecular orbital. And so here we're not drawing the shape of the molecular orbital, we're just putting in an energy line, because for this purpose, that's all we care about. Okay, so we have a molecular orbital at every single vertice, and that's it. That's actually the energy levels for the molecular orbitals. And then what we can do is fill in the number of electrons that we're dealing with. So for benzene, we have 6 pi electrons, and so we can put them in. course, we're going to put them into the lowest energy molecular orbitals, so 2 go into that most stable orbital, and then 2 each in that next set of degenerate orbitals. And that's it. That's the MO diagram of benzene, and it's just that easy. So keep in mind that that dotted line is the zero energy line, so anything below that is going to be a bonding orbital that's going to be favorable for electrons to go into it, and anything above is going to be anti-bonding, so we wouldn't want to put electrons up there. And so you can see in benzene that all 6 electrons are paired, which is good, and they're all in rather stable bonding orbitals. And so, as we know, benzene is aromatic, okay? Let's look at another one. Let's look at cyclobutadiene, okay? So again, we're combining single carbon atoms with p orbitals, each with an electron. In this case, 4 of those. We're going to build up the molecular orbital diagram of cyclobutadiene. So we have our dotted line, we have our circle, and we're going to inscribe a square into that, okay? And which I neglected to mention is that one vertice is always down, and that's because we always have that lowest energy molecular orbital. So here we have a square tipped on its side, and we're just going to put a molecular orbital at each of those vertices, okay? And now you can see we have 4 electrons we need to fill. The first 2 can go into that lowest energy molecular orbital, so that's actually great. This is a deeply stable molecular orbital, but the next 2 have to go into that next degenerate pair, as we saw before. So that not only leads to these unpaired electrons, but you can see now that those 2 molecular orbitals actually exist at the non-bonding level, 0 energy. So they're no more stable being incorporated within this molecule than they would have been just floating free on their own. In fact, they're actually worse in the cyclic form of this 4-carbon conjugated system than they would have been if they were just left to be acyclic, right? So in this case, being cyclic is much worse, right? So that's why the 4 pi electrons is not one of the Huckel numbers. And so we can see 4 electrons, 2 unpaired in non-bonding orbitals. This is a terrible situation. Cyclobutadiene is extremely reactive, and in fact it's so reactive it's called anti-aromatic, right? So we have aromatic and now we have anti-aromatic. It's sort of like the evil twin of aromaticity, and we're going to talk a little bit in more detail about anti-aromaticity in the next lecture.